All right, let's get into it. So far, we've looked at how differential equations describe a system's own natural rhythm. But what happens when some outside force comes along and starts pushing things around? Well, that's the whole puzzle of non-homogeneous equations. And today, we are going to crack them wide open with a method that's, frankly, pretty elegant. So here's our game plan. First, we're going to see what makes these new equations tick. Then, I'll show you the two-part master plan for finding the solution. After that, we get to the fun part, the art of the educated guess. And maybe most importantly, we'll cover the critical fix for when our guess runs into a very specific kind of trouble. So what's the big deal here? Well, up until now, our equations have pretty much always been set equal to zero. Today, we're throwing that zero out and replacing it with an actual function. We call this the forcing term, and it lets us see how a system actually responds when it's being pushed or pulled by something. And this slide, this really nails the T difference. On the left, you've got the homogeneous equation, the one that equals zero. That's just the system doing its own thing, totally unforced. But on the right, you see it equals g of x. That g of x is some active external force, and the whole equation describes how the system reacts to it. Okay, so how in the world do we solve these things? Well, it turns out there's a master key. There's this fantastic theorem that tells us that every single solution is built from two totally separate parts that we find on their own, and then we just add them together at the end. So this first part should look pretty familiar. It's the complementary solution, which we call YC. To find it, you just pretend that g of x isn't there, set the right side to 0, and solve it just like you always have. This is the system's baseline, its natural behavior. Now, the new piece of the puzzle is what we call the particular solution, YP. All this is any single solution, it doesn't matter which one, that works for the full non-homogeneous equation. Think of it as one specific example of how the system responds to that outside force, g of x. And here is the big idea, the thing that makes it all work. The complete general solution is always just the sum of those two parts. It's the system's natural behavior, YC, plus its specific response to the force, YP. That's it. Y equals YC plus YP. So, what this all boils down to is a really simple three-step workflow for every single problem. Step 1, find YC. Step 2, find YP. Step 3, add them together. It's structured, it's simple, and it works every time. Finding YC is old news, right? We know how to do that. But how do we find YP? Well, this is where the magic comes in. Instead of some super complicated formula, it turns out that for most common types of forcing functions, we can just make a really, really smart guess. I mean, think about it for a second. If that forcing term, g of x, is a polynomial, what are its derivatives? They're also polynomials. So it kind of makes sense that the solution, YP, that has to balance everything out, is probably going to be a polynomial too. The same logic holds for exponentials and sines and cosines. The response should probably look a lot like the force. And this slide, this is basically our playbook. It's the cheat sheet for making that educated guess. If g of x is a polynomial, you guess a general polynomial. If it's an exponential, you guess an exponential. But notice this one key detail. If you see a sine or a cosine, you have to guess a combination of both. Why? Because their derivatives keep flipping back and forth between each other. Okay, that's all well and good for simple forcing functions. But what if g of x is more complicated? Like, what if it's a polynomial plus a sine wave? Well, there's a really clever trick for that. Since these equations are linear, we get to use something called the principle of superposition. And all that means is we can break a big, messy problem down into smaller, much easier ones. You just find the particular solution for the polynomial part, then you find the solution for the sine part, and at the very end, you just add them together. It's a classic divide and conquer strategy. All right, listen up, because this is probably the most important part of this whole method. There is one potential trap that can completely stop you in your tracks, but the fix is actually surprisingly simple. Getting this right is what really separates the pros from the novices. This is the million-dollar question. What on earth happens when the system's natural behavior, the YC part, already looks exactly like the force we're trying to apply? Our standard guess becomes, well, it becomes redundant. It's already part of the homogeneous solution, so it can't possibly work for the other side. Just look at this example. Our complementary solution, YC, already has an e to the x term in it. So when we make our normal guess of a times e to the x for our particular solution and plug it into the left side of the equation, the whole thing just cancels out and becomes 0. And that leaves us with the impossible statement that 0 equals a e to the x. That's a big red flag. Our guess has failed. This situation has a name. It's called resonance. It's what happens when there's that critical overlap between your trial yp and the complementary solution yc. You know, in physics, it's like pushing a swing at its natural frequency. The response just goes wild. Here in the math, it means our standard guessing method just completely falls apart. And here's the fix. Honestly, it's so simple it almost feels like cheating. If your guess overlaps with dy, you just multiply that guess by x. If it still overlaps, you multiply by x again. You just keep going until it's unique. Why does this work? Because multiplying by x creates a new function that's mathematically independent from the original term. It's a clever little sidestep that gives us a new guess that won't get canceled out. So let's go back to our problem. Our first guess, a times e to the x, failed miserably. So we apply the fix. We multiply by x. Our new, corrected guess is a times x times e to the x. Now that term is not in yc, and when we plug this new guy into the equation, it doesn't just vanish to 0 anymore, and we can easily solve for a. And just like that, problem solved. And we need to remember, this isn't just some abstract theoretical game. This is a powerful tool that we use to solve real-world problems with initial conditions, and it even works perfectly for more complex, higher-order systems. So if you have an initial value problem, an IVP, the process is exactly the same. You just have one extra step at the very end. First, you find that full general solution, y equals yc plus yp, and it's going to have those c1 and c2 constants floating around. Then you just plug in the initial values you were given to solve for those constants and pin down the one unique solution that fits. Okay, let's wrap this all up with the 4 big rules of the game. Rule 1, always find yc first. You absolutely need it to check for resonance. Rule 2, make your guess for yp based on the form of g of x. Rule 3, check for that resonance. If your guess overlaps with yc, you know the fix, multiply by x. And rule 4, if g of x is a sum of things, just use superposition to divide and conquer. Follow these rules in this order, and you will solve the puzzle every single time. And that leaves us with one final lingering thought. This method of undetermined coefficients, it's a fantastic shortcut. It's fast, it's efficient, but it only works if that forcing term, g of x, is one of these nice, predictable functions. So, what happens when it's not? What if g of x is, say, a tangent function or a logarithm? Well, that's a puzzle for another day.